I propose we get started. I'm not sure our numbers will climb much higher than this with career fair.
Great.
Okay. How are folks doing? Is lab 1 going okay? You know, I talked to Andrew a little bit about it. Anyone have an integrator running yet? By chance? If not, that's okay. But start working on it if you haven't. And when you do, remember to do things like take screenshots. Future you will thank you if you do that, so you don't have to go do that again. Today's lab section there's only one group in today's lab section. So if any of the Friday sections would like to attend today, you're more than welcome to. There's still only 5 in the Friday section, so it's not like we're overly crowded. But if you want an extra day, you're welcome to come join the Wednesday section, okay? Any questions about anything? Seemed to go okay, the Monday lab. A few minor annoyances here and there and some things to get used to, but overall, I don't know. Monday lab seemed okay, right? Folks that were there? Okay.
Yeah, it seemed all right.
Cool. So what I thought I'd do today is go over some lab 1 content, talking more specifically about the equations that we're going to be building the integrators for, and the hardware that we're actually going to end up building. And I'm going to do that similar to like I did a couple lectures ago by sharing a Jupyter notebook with you all. So I thought I would start by just briefly reviewing Euler integration specifically for the Lorenz equations. Again, something I'm sure that you've seen before, you've seen this concept before, but it may have been a few years since you've done something like this, so perhaps worthwhile to just review it. So let me start by recall the equations in question. So these are the equations that we're actually going to be integrating. So we have x dot, which is a function of time. I'll use subscript t just to make it a little more readable, equals the parameter sigma times y minus x. Y dot equals x times the parameter rho minus z minus y. And then z dot equals x times y minus the parameter beta times z. And let me just make all these line up. So these are the equations that we're integrating. Where, like I said, all of the derivatives are functions of time, and then the variables x, y, and z are all functions of time as well. So there are a lot of ways to do numeric integration. Whole books written on the topic in sort of increasing levels of fanciness. We are going to be doing perhaps the least fancy version of numeric integration out there, which is a first order Euler integrator. So suppose that we know the initial conditions for x, y, and z. So suppose that we know x at, I'll do it this way, x at t0, y at t0, and z at t0. And suppose that we know all parameter values. What we want to calculate then is, so we want to know the following, which I'll put in their own separate block, but we want to know x at t0 plus some delta t, y at t0 so plus some delta t, and z at t0 plus some delta t. Now, at this point in your academic careers, you should be looking at some expressions like that, x at t0 plus some small deviation, and every muscle in your body should just be aching to Taylor expand it, right? You're just dying to Taylor expand something like that. So that's exactly what we're going to do. So we could calculate these values via a Taylor expansion. So we know that, it's the same for all of them. So just to save time, I'll just consider x. So we know that x at t0 plus, x at t0 plus some delta t is exactly equal to the sum of an infinite number of terms. So the first in that infinite series of terms is x at t0 x at t0. The next one is x dot at t0 times delta t plus infinity more terms that I will wrap up into the expression HOT, or higher order terms. Right, you've all seen Taylor expansions before. So the next one would be, if we were to write it out, 1/2 times x double dot times delta t squared, et cetera, et cetera, et cetera, for higher and higher orders of delta t. And we're making the assumption that this time step delta t is small enough that everything above linear delta t is negligibly small. So it's small enough that if you square it, the resulting number is so tiny that we can safely ignore it. So for Euler integration, we ignore all higher order terms, HOT, which yields the following. So then we get essentially this expression. We say that x at t0 plus delta t is not exactly equal to, but approximately equal to, close enough to just that first term, ignoring all the higher order expressions. And then the same is true for y and for z. So we have a similar expression for y. And then we have a similar expression for z. Where conveniently, these x dot, y dot, and z dot terms, these are the Lorenz equations that we already have, right? So the notion is that if we know the initial conditions, x at t0, y at t0, and z at t0, we can substitute those into our differential equations to calculate x dot, y dot, and z dot at t0, and calculate x, y, and z at the next time step, and so on, right? So then if we want to calculate it at, so that would give us x, y, and z at t1. If we wanted t2, then we would do exactly the same thing, substitute x at t1 in for all these expressions, calculate x dot, y dot, and z dot at t1 multiplied by delta t, and so on and so on and so on. Anything I want to say about this? In practice, when you all implement this, by judicious choice, by strategic choice of your time step delta t, that can be a shift instead of a multiply. Right, so it'll be some small number, and we can talk about the appropriate sort of ranges of options for numbers to choose for delta t. But if you make this time step delta t a power of 2, then instead of using a multiply here, when you implement this in Verilog, you can instead use a shift. Okay. Any questions about this?
Do you think you could clarify what you mean, what the dot notation above the x, y, z means?
Yeah, sure. So notation clarification. So yeah, that's the dot is, who came up with the dot notation? I think that was Newton's thing. I think Newton liked dots, but it just means the following. Dot x is the same as derivative with respect to time of x. Okay. It's just a little more tidy. Any other questions? Okay. The next thing I wanted to go over in connection with Lab 1 is fixed point representation. And in particular, 7.20 representation, because that's what's recommended for Lab 1. So let's start by, let's just take a look at this. Take a look at this. We can look at a picture of visual representation. So we're using 7.20 fixed point representation, which means the total size of the register which holds our value is 27 bits wide, where we assume that the decimal is between positions, 19 and 20. So that is to say, we have 20 bits below our decimal and 6 bits above our decimal. So this gives us a range of plus or minus 63, and then a delta of approximately 10 to the minus 6. What do I want to say about this? I think that's all I want to say about this. I'm going to talk about how to multiply these things in a moment. So let's take a look at signed multiplication. Multiplication of 7.20 fixed point. And I'm going to grab a code snippet from the website. So if we go to the web page for Lab 1, there is a snippet here, right here, that includes a simple integrator that I'm going to talk about in a little bit. But for now, I just want to consider this integrator, which I'll just put in here so that we can have syntax highlighting. So I thought I would show you the Verilog first and then talk about why this is the way that it is. But this is a module that will do signed multiplication of two 7.20 fixed point values. There's not that much going on in here. All that happens is it takes in two inputs, A and B. Sorry, am I missing chats? Oh, thank you, Katie and Bruce. Sorry, I was missing those. So it takes in two inputs, A and B, each of which are 27 bits wide in assumed 7.20 fixed format. And then it'll return an output of the same type. It does so by doing a multiplication of these two numbers and storing that in an intermediate register called mult_out, which is 54 bits wide. So twice the width of both of the inputs. And then it returns the most significant bit, bit 53, and then this range of bits 45 to 20. And I want to show you why that's the case, why it's grabbing those bits in particular. So we can take a look at an image here. So if we suppose that we are multiplying two 7.20 fixed variables, Okay, so that is to say that the decimal point is between bits 19 and 20 for each of these values. When we do that first multiplication, so this line here, when we're just multiplying those two numbers, we will get the result of that multiplication will be a value that is twice as wide as both of the inputs. So it'll be a 54-bit wide register where 14 bits will be above the decimal and 40 bits will be below the decimal. So in the output, the decimal, after multiplication of these two fixed point numbers, will be between bits 39 and 40. These two numbers that we multiplied both had 7 bits above the decimal, so the resulting output has twice that, 14 above the decimal, and they each had 20 below, so the resulting output has 40, which is twice that below. So then why are we grabbing these specific numbers? Because these are signed inputs, they're being represented in 2's complement. So the sign bit lives in the uppermost, the most significant bit of this value. So we grab that to retain the sign of the output. And then we want to grab the 6 bits directly above this decimal and the 20 bits directly below that decimal. So if the decimal lives between bits 39 and 40, that means we want to grab bit 45 down to 20. So we want to grab the bits directly adjacent to the decimal point. Does this make sense? So suppose that these were not 7.20, but in future labs you will use, I think the next lab we use 2.16 fixed point. So that means 2 bits above the decimal, 16 bits below the decimal. If we were to multiply 2 of those, the intermediate output would have 4 bits above the decimal and 32 bits below the decimal, right? So we would have to, if you are building one of these multiplier modules, you have to think carefully about which bits you're selecting. It's an easy mistake to make, right? So these specific numbers depend on the size of the registers that you're multiplying. Okay. And by the way, I was talking to Andrew about this before the start of this lecture. In lab 1, it's recommended that ultimately for lab 1, you need to be able to set the values of the constants and the initial conditions from the command line. It's recommended that you start by just hard coding those things. Remember that you need to hard code them in 7.20 format. I've done this lab a few times now. Every single time I've done it, I've made that mistake. You need to think very consciously about, okay, I'm trying to represent the value, whatever it might be. One of the values is like 8/3, one's 28, I think. Just think carefully about where your decimal point actually lives so that you build these constants properly. Otherwise, you can get some weird symptoms. Get some weird behavior out of your output. All right, I'm just going to make a note of that. Be careful to hard code. Be careful when hard coding parameter values that you are using. 7.20. A very easy mistake to make. Questions about this stuff? Okay. I wanted to briefly mention two converting from float to fix, both directions. I'm going to let you sort of think about this a little bit, but we might have something like float to fix some input A is going to be I'll let you think about why this is. It looks like an arbitrary number. It's not. It has to do with, if you think about the number 1 in 7.20 format, okay, which means that there's a 1 at this bit right here, 1 right above in bit number 20. Think about what that number equals if you're not assuming fixed.20 format, right? Which is to say, if bit 1 were actually the least significant bit, as it usually is, and that number will make a lot more sense. And going the other direction, fixed to float for some A is going to be float A divided by 1048576. Oops. 1048576.
This is code for the HPS.
Yeah, correct. Yeah. So you'll have these sorts of conversions on the HPS side. So in Verilog, you're using 7.20 fixed point. You're going to sign extend that to a 32-bit integer to communicate it over to the HPS. And when you receive it on the HPS side, you want to do floating point stuff with it. So you'll have to convert from fixed to float. And then conversely, when you enter the values for your parameters and initial conditions on the HPS, you'll convert that from float to fixed before communicating it over to the FPGA. So this is where these conversions live. Okay. So any other questions? I want to next talk about the integrator. So let's look at the basic structure of an integrator. And let's do this just by, I'm going to show a picture. So this is the basic picture of what your integrator is going to look like. You're going to have some modules that will take in the current values for X, Y, and Z and use those values in order to calculate the derivatives at that particular time step, X dot, Y dot, and Z dot. Multiply by dt, and then add with either, this is an implementation of these equations up here, right? So what we're doing is calculating these derivatives and multiplying by dt, and then adding with the current value of X, Y, and Z, where you want to be able to pass in initial conditions as well, right? So there's a multiplexer here that allows you to pass in the initial conditions for X, Y, and Z, or alternatively, to pass back the values that you just calculated. And your previous value then gets stored in this clocked register. So when you clock this register, you get the new values for X, Y, and Z at time step k plus 1. And you do all this again. This clock, by the way, you're probably going to be clocking this integrator from the HPS, probably. So this will be something like a parallel I/O port, which I haven't talked about yet in lecture, but that'll be the topic of the next, either the next lecture or the one after that. Okay. I want to take a look at in the Lab 1 webpage, there's an integrator code snippet that I thought we could talk through. This is a very simple example of an integrator, but it's the basic structure that we are building in Lab 1. So in this case, the function that we're integrating is just a constant. And so the expected output of this integrator would just be a constant ramp, right? Because when you integrate a constant, you just get that constant time to time. So this module is, we can look at the inputs and outputs. It's outputting a 27-bit 7.20 fixed point number. It has an input called funct. This is the dv/dt function. So for you, this will be this will likely live in a separate module. You'll likely have some module that's calculating the derivatives that you'll tie to this integrator module. In this case, that's just getting passed in as an input. Has a clock and reset line, and it has initial conditions and some intermediate values here. And we can look at all this. All that this does is at each positive edge of the clock, if low reset, interesting. So if reset is 0 in this particular case, then the value of V1 gets the initial conditions. Otherwise, V1 gets the value contained in this register V1 new, where for all time, the value of that register V1 new, at all times I should say, is being assigned the current value of V1 plus the dv/dt function, funct. And then we're assigning the output value of V1. So if you think about this, suppose we're not in reset and a rising clock edge happens. What will happen is the value that is being held in V1 new will be shifted into V1, which means our output will change. Our output will become that new value of V1. And since this also changes, V1 new will also assume a new value. So this will ramp up and then it'll ultimately overflow and ramp up again. So your integrators will look a lot like this. What will likely be different is this line. Probably this will be, you will likely have your integrator module tied potentially to some separate module that's calculating. You might not do it this way, but the way I expect many of you will do it is have a separate module that's constantly calculating derivative values and tying your new output of your integrator to that separate module. But structurally, your integrator will look like this. Okay. Any questions? I feel like I'm moving off I feel like I'm going through this at a lot of speed. So hopefully that's okay. You can interrupt me if you want. I'm getting through my notes for today faster than I expected. I'm not sure what that means, but it's happening. So let's take a look specifically at one of our, take a look at one of our state variables in particular. So let's look at the hardware for X. So what I want to do is look at the hardware being built specifically for our X state variable. Oops. So that's going to look like, okay, where in the previous picture that I showed, I said that we had some module here that was constantly calculating the derivatives x dot, y dot, and z dot. All I'm doing now is adding some details for the x dot calculation so that we can see what that looks like. So in the case of the x dot calculation, you'll recall from the equations above, let me just copy those down to here so that we can look at them at the same time. So this is the hardware implementation of this first differential equation, the integration of this first differential equation. So you can see that x dot is sigma times the difference of y and x. So here we have our state variables y and x. We're calculating the difference between those two, multiplying by sigma, and then doing the Euler integration, which is to say multiply that derivative times our time step, and then add the previous value of our state variable, xk. So the output of this, xk plus 1, is going to be xk plus dt times x dot at time step k. This is the hardware implementation of that logic. Okay. And then just for fun, we can look at the hardware for the whole system, which is a more complicated picture, but it's maybe useful to see. So up here, you can see I have y sort of going ... off, not pictured here, the calculation of that y. Here I have everything connected. So this is the full hardware picture of the integrator that you're going to be building for lab 1, where you have x, y, and z coming in. You have your parameters rho, beta, and sigma. Everything before these dt multiplications, so everything here and to the left, is the calculation of the derivatives for x dot, y dot, and z dot. And then we're multiplying those derivatives by dt and adding to x, y, or z of that current time step to get our outputs. X at k plus 1, y at k plus 1, and z at k plus 1. And those are fed back so that we can calculate the subsequent time step. And they're also communicated over to the ARM for visualization on the VGA. I'm going to talk about this communication to the ARM in probably the next lecture. But this is what you'll be building in ModelSim, which is kind of useful. I mean, it's a good reminder, I think, when I was putting this together. It's a good reminder of the complexity of the stuff that you can build so quickly in Verilog. This is a lot of hardware, and when you actually write this out in Verilog, you'll find that it's not that much code. It's just, I don't know, gives me kind of a powerful feeling or something. So maybe it does that for you too. I'm not sure. In any case, do folks have questions? This went far faster than I was expecting, so I'm happy to answer questions. Okay. Anyone have any final project ideas? Not too early to start thinking about that at all. It's closer than you might think. It's maybe 8 weeks away or so. So start pondering. Maybe start going through the website and looking at previous year's projects. Some things this semester will be probably difficult given our remote setup. So things involving, there are a lot of previous projects that involve sort of pointing the camera at people and doing processing on camera data. That might not be, it's not obvious precisely how that could work remotely, but you have access to the VGA screen. You'll be able to see the VGA screen. So any kind of physics or computer graphics project you would want to do is perfectly fair game. Audio projects are perfectly fair game. So start thinking about it. Okay. If there are no questions, that's all I have. Bruce?
I got a question for the group. So multiply, the implementation of multiply depends in detail on the number of bits in the fraction. What about add and subtract? how does add and subtract work with fixed point versus integer? It's a trick question. There is no difference.
Okay. I'm just scrolling through. Stop me if you want to talk about anything.
Actually, I had a question about the integrator module.
Okay.
I think you mentioned something about the assign v1 u equals v1 plus func line. I think I missed what you said about it.
This is the equivalent of the Euler integration that we're doing. In this case, all that's happening here is we're integrating a constant. So at the new time step, the value of this variable v1 will be given by the previous value plus some constant. In your case, I was just saying that this is the line that will be the most different between this implementation of an integrator and your implementation of the Lorenz integrators. This funct here is this is here in the place of dt times the derivative.
Right.
So in the place of this funct, you will have dt times the derivative. And what I was saying about that is exactly how you put that together structurally is up to you. It might be the case that you have a separate module calculating those derivatives.
And then just passing that into the module.
Yeah, yeah.
Okay.
It's up to you, of course, but I expect that that's how many people will do it.
Okay, just wanted to double check because I remember you like mentioned something about it and I didn't quite catch what you said. But
Sure.
That makes sense. Thank you.
Okay.
For reasons that escape me, I think when I first wrote this code, I put the DT shift into the parameter call of the module itself, rather than passing in the shift amount as a parameter.
Sure. Can look at lab 1 here. Anything else to mention about lab 1? As folks have read through this, if any questions have come up, you can feel free to ask them.
So just to clarify, the inputs from the HPS to the FPGA for the final implementation will be the initial conditions and DT. Is there any, should the FPGA be keeping track of like the current state?
So you'll pass in the initial conditions and the parameter values for sigma, rho, and beta.
Mm-hmm.
I don't believe it's required that you pass in DT.
Okay, so that can be
okay with that
hard-coded.
being hard-coded. Bruce, can you concur? Or is that a parameter that you want passed in?
Go either way. I think you could treat it as a constant as long as, because since the dynamics is fixed here, you could probably guess that the DT could be fixed as long as you don't mess with sigma too much. You could write it so that you pass it in as an integer from like 7, meaning shift 7 bits. But that's a choice about how you want to write the user interface.
Okay. I will stay on on the line here until 1:30 in case any folks want to hang out and ask specific questions. Otherwise, you can feel free to sign off, and I will see you all on Friday, if not before.